Imagine an oil refinery, a complex and efficient system designed to process and distribute oil. These plants are essential to human life all over the planet, from powering the car we drive to supplying products people put in their hair. At the core of this refinery are the large storage tanks. Oil from these tanks is then transferred through intermediate containers. These containers manage the flow of oil throughout the refinery, ensuring it reaches different processing units efficiently. What happens if this well-organized system of storage fails? Imagine the refinery without these essential storage components. Oil would spill everywhere, causing chaos and halting production. The refinery's efficiency would plummet and nothing would get processed correctly. Just like this refinery, a computer depends on a structured system to manage data efficiently. Data is held long-term in non-volatile storage units referred to as secondary storage. The most popular forms are HDDs and SSDs. Next, you have a memory system. These are the components that take data from the storage unit so that it can be worked on by the CPU. Lastly, you have deposits where the data resides within the CPU. These are called registers and hold very small amounts of data, typically only the data that the computer needs to perform the next instructions. The focus of this video is going to be on the memory system and how it works. In this video, we'll cover the following topics. We'll start by looking at a brief history of memory and computer systems. Next, we'll explore how memory works. Then we'll introduce some important concepts related to memory. Lastly, we'll examine a recent innovation in memory technology, and we'll conclude by describing a significant challenge in modern memory systems. Before getting further into this video, I want to make note of the resources used to make this video. Due to the scope of this being relatively high level, I relied heavily on textbooks and less modern academic papers, which can be seen on the screen right now. Images and diagrams were either created by myself, created using DALL-E, or from a common license image, which can be linked in the description below. Our journey through the history of computer memory begins with Charles Babbage's analytical engine, conceived in the early 1830s. Babbage designed this mechanical computer to use punch cards for input and output. It was inspired by the Jacquard loom, a machine made in the 18th century to loom based off an input of rotating punch cards. Gustav Salchek invented drum memory in 1932. Note that's not the drum on screen. The drum was a metal cylinder coated with a magnetic material, with data being written to and read from the surface as it rotated. Each drum could store thousands of bits of information, making it a significant improvement over existing technologies like the punch card. The 1940s saw the advent of electronic computers, such as the ENIAC developed by the US government in World War II, which used vacuum tubes for processing data, but the ENIAC relied on mercury delay lines and punched cards for data storage, marking a significant shift from mechanical to electronic memory. However, drum memory was still more popular at the time, and advancements in drum memory technology continued throughout the 1940s and 50s, with increased storage capacity and speeds. This technology became a staple in early computers, providing a reliable means of data storage and retrieval. The invention of the integrated circuit in 1958 and the silicon implementation of the integrated circuit revolutionized memory technology, leading to the development of semiconductor memory. In the early 1960s, static random access memory, or SRAM, was introduced based off of semiconductor technology. In 1968, Robert Dennard invented dynamic random access memory, or DRAM. Today, we use improved versions of these original DRAM and SRAM to facilitate the flow of data between storage devices and the CPU. These advancements have provided unprecedented speed, capacity, and reliability, becoming essential for the high-performance computing environments of the modern era. Now that we know about the history that brought us to our current state, how is data actually transferred through a modern computer? Let's start with a high-level example where we have some data stored in our storage unit and we want to bring it to the CPU accumulator. The CPU reads some instruction that requires reading data from storage. It then results in the operating system interpreting a request from the CPU to get data from the storage unit, in our example, a hard drive disk. The hard drive disk then performs some work to get the data from the position specified. That data is then transferred to the main memory unit of the memory system, the RAM, via the system bus, a series of wires within the computer. Once in the memory system, the CPU can now access the data in the memory system via its series of buses to facilitate the movement of data. With this high-level understanding of what the memory system does in the broader context of a computer, let's take a look at how the memory system works to actually carry this out. To start off, the memory system is composed of two main units which can be classified into the main memory unit and the various caches. The main difference between how the two work is in the substrate of how they are made. That is, what form of RAM do they implement? To begin, we'll be looking at how the main memory unit works. The main memory unit refers to the fundamental component of the memory system where all the working data can be found. Whenever we think of RAM and buying some 16 GB RAM for our computer, this RAM stick is what composes the main unit of the memory system. As we said before, the main memory unit is made from a different substrate than caches. Specifically, it implements dynamic random access memory, known as DRAM. DRAM is composed of multiple DRAM chips, each containing millions of DRAM cells. A DRAM cell is the fundamental building block of DRAM, consisting of a capacitor and a transistor. The capacitor stores 1 bit of data as an electrical charge, while the transistor acts as a switch, allowing access to the charge within the capacitor. DRAM is organized into a hierarchical structure. At the lowest level, we have the DRAM cells, which are grouped into rows and columns to form up a memory array. Multiple arrays of DRAM cells are combined to form a memory bank. In this image, each little square is an individual DRAM cell, while each of the vertically grouped cells represents a bank. Each DRAM chip can contain several banks, which allow for simultaneous access to different banks in the memory, improving performance. These banks are then grouped and connected to memory channels. A memory channel is an independent pathway between the DRAM module and the CPU. Modern systems often use dual-channel or even quad-channel memory configurations to further enhance data transfer rates. Lastly, it's important to understand that due to one transistor, one capacitor makeup of the DRAM cell, the charge held in all the capacitors degenerates over time. In order to ensure no data is lost, this requires the DRAM to perform what is called refreshing on a recurring basis, usually every 64 milliseconds. This process affects every row in the memory, one after the other. It essentially works by first detecting whether the charge in a cell is closer to 0 or 1, and then it either provides a positive charge to get it back up to 1, or bring it lower to 0 if it was meant to hold a 0. Now that we know the makeup of DRAM, we can learn how data is actually transferred to and from the CPU. To illustrate, we'll be using an example of reading some data at memory address 0x0200F111. First, the CPU signals for the specified address on the address bus and sets the read enable flag on the control bus to read the data. The first segment of the address will correspond to one of the banks in an individual DRAM chip in the DRAM. In this case, 02 denotes bank 2, highlighted in gray in our example in the bottom left. The remaining part of the address is then used by the row decoder and the column multiplexer and column decoder to access the specific location within that bank. In this case, the row decoder sent a charge on the word line for row 00F, denoted in blue. This means that the transistor gate for every DRAM cell in that row is now turned on, connecting the charge held in the capacitor to their respective bit lines. Next, the column address, denoted in pink, is used by the column decoder and multiplexer. They select the specific bit lines from the address to activate and connect to the DRAM's output. These are denoted in pink. The final result is that the charges from all the DRAM cells that correspond to the bit line and word line intersection, denoted in the green overlap between the pink and the blue, are sent through the bus and into the CPU. In this case, our address corresponds to a 4 bits of binary that represents in the decimal integer 5 or 0101 in binary. Now that we've explored how DRAM works, let's turn our attention to another type of memory, static random access memory, or SRAM. The conceptual organization and function of SRAM is similar to DRAM, but there are some important differences to understand. While DRAM relies on capacitors and transistors requiring constant refreshing to retain the data, SRAM takes a different approach. SRAM cells are made up of multiple transistors to store each bit, forming a flip-flop circuit that does not require refreshing. This is a significant reason for why SRAM is much faster to access, as there are no instances of a refresh that could block the incoming access of some row in memory. However, due to SRAM requiring more transistors, it requires more physical space to hold the same capacity of data. Specifically, SRAM memory is able to be accessed more than 20 times faster than DRAM and up to 100 times faster, but this does not come without a cost. The actual cost of implementing a memory unit for each of these substrates differs substantially. For implementing 1 GB of SRAM, it is between $500 to $1,000, about 100 times more expensive than DRAM. So to conclude, we now have two very differing substrates to create memory. one where you are paying about 100 times more to get almost 100 times faster access. This brings us to an important concept in the memory systems that will help us understand where we would use one type of RAM versus the other. Let's delve into how these two memory types fit into the memory system of a computer. We already know that DRAM is used to produce memory sticks that occupy the main memory, but where does SRAM come in? To explain, we need to understand what is the memory hierarchy. The memory hierarchy is how we organize all the different components in the system's memory system. That is, components that facilitate the storage of data. The hierarchy is organized with the fastest components at the top and the slowest components at the bottom. For example, it takes a long time for the CPU to access data in the storage unit, like an HDD, resulting in it being at the lowest level, whereas the CPU can almost instantaneously read data from its CPU registers, putting it at the top of the hierarchy. The main memory plays an important part in this system. It holds the data from the storage device in a format that is easily workable by the CPU. However, the main memory unit is made from DRAM, and as we learned before, DRAM is really good at storing working data at a low cost and a high capacity, but SRAM is much faster. So how do we make use of SRAM to speed up the data reading and writing process in a computer? We use a concept called caching. Caching is when you take some portion of a greater body of items and make that portion easier to access. The purpose behind that is that some items from a group of items need to be used more frequently than other items from that group. So instead of having the user of those items go through the same amount of work to get any item, we segment the most frequently used items in a way that is easier to access. This isn't unique to computer memory. We do it in many aspects of life, such as keeping our favorite shirts in the most accessible part of our closet, or when a website caches certain specific pages that are much more popular, so it doesn't need to load the page from scratch every time. So how is caching implemented in a computer memory? It makes use of SRAM to create caches. These are individual units within the memory system, often on the CPU, that are meant to take data from the main memory unit so that the processor can access the data much faster than it would be able to otherwise. Furthermore, there are many layers of caches implemented in modern computers. These are organized into layers, where modern caches make use of many strategies to determine what data to hold. But two of the most important principles are those of locality. Firstly, temporal locality. That states that a memory address that was addressed recently will tend to be addressed again soon in the future. And secondly, spatial locality. If a memory address was addressed, addresses close to that address will also tend to be addressed soon enough. Through use of these principles and other tools and algorithms, the caches in a memory system intelligently store data that will be more frequently used by the CPU. To understand how a cache maps to a memory address, let's first discuss the concept of blocks in the cache. The main memory is divided into fixed-size blocks, and these blocks are mapped to the cache. Each block in the main memory can be stored in one or more blocks in the cache. The process of determining which cache block a particular memory block will occupy is known as cache mapping. There are three primary cache mapping techniques: direct mapping, associative mapping, and set associative mapping. In direct mapping, each block of memory maps to exactly one cache line. The memory address is divided into three parts: the tag, the cache line, and the block offset. The cache line determines where the memory block is stored in the cache, and the tag is used to identify if the block in the cache is a desired block from main memory or if it's storing an other block. Associative mapping is a more flexible technique, allowing any block of memory to be stored in any cache line. The memory address is divided into two parts here: the tag and the block offset. The tag is used to search the entire cache to find the corresponding block. Set associative mapping is a compromise between direct and associative mapping. The cache is divided into several sets, and each block of memory maps to a specific set but can be placed in any line within that set. The memory address is divided into the tag, the set index, and the block offset. Each of these techniques have their pros and cons. For example, direct mapping is much easier to search as any address from the main memory can only exist in one cache line, whereas in associative mapping, we have to search every cache line, but it allows us a greater degree of freedom in using all the lines in the cache. So how does the cache actually pull in the address from the main memory? This brings up the idea of hits and misses. A hit occurs when the CPU searches for the address and it is found in the cache. A miss occurs when we don't find it in the cache, and a hit is quite simple to handle as the CPU just reads in the data from the cache line that corresponds to the memory we need. However, in a miss, we need to pull in that data from the main memory to the cache so that the CPU can access it from the cache. This results in a much slower time to retrieve the data. These misses can significantly increase the latency of a cache. Modern techniques to optimize how we deal with misses are out of scope for this video, but further learning can be found in the description below. When it comes to using data in computing, we care about two things. Firstly, we want to be able to use a lot of data, and secondly, we want to be able to use that data very quickly. In that respect, there are three concepts that are important to understand. First is latency. How long does it take the processor to access data from the memory unit? Secondly is parallelism. How many accesses can be made by the processor to that memory unit at any one given time? Lastly is bandwidth. How much data can the processor access from the memory unit in some period of time? With these concepts, we're able to measure the performance of a unit in the memory system in the form of its bandwidth. This can be measured by dividing the amount of accesses it can make at any one given time by the amount of time it takes to make that access. For example, imagine in our example that we can make one access of 8 bytes at a time, with every access taking about 1 second. In this example, our bandwidth would then be about 8 bytes per second. In recent years, the core count on CPUs has increased almost exponentially. While modern memory system technology has successfully provided bandwidth to these additional cores, enabling multi-core CPUs to achieve greater computing power, the bandwidth per core has remained relatively constant. In 2019, Micron introduced DDR5, the latest innovation in DRAM design. DDR5 plays a crucial role in modern computing, addressing some bandwidth constraints of previous DRAM technology like DDR4 and its predecessors. DDR5 significantly improves the megatransfer rate, measured in megatransfers per second, i.e. the previous bandwidth measure that we looked at, but measured in data transfers per second instead of bytes per second, and it's increased ranging from 3,200 megatransfers per second to 6,400, compared to DDR4, which had a range of about 1,600 to 3,200 megatransfers per second. To further elaborate, at 3,200 megatransfers per second, DDR5 can achieve a bandwidth of 2.85 gigabytes per second to a 64-core CPU, compared to DDR4, which can only deliver a 2.1 gigabyte per second bandwidth. At the max transfer rate of about 6,400 megatransfers per second, DDR5's bandwidth reaches up to 4.66 gigabytes per second, significantly enhancing the data transfer capabilities. DDR5 achieves these advancements through various technologies and innovations, most notably increased DRAM cell density. This not only boosts the megatransfer rate, but also expands the overall memory capacity, allowing for higher RAM capacities in computing systems. As data availability, processing power, and data needs continue to grow exponentially, advancements in RAM architecture, like DDR5, are essential. These improvements help prevent memory system bottlenecks, ensuring that investments in other areas of computing are not hindered by memory limitations. With an understanding of the importance of DDR5, let's explore a little bit more about how these advancements came to be and the issues surrounding them. While Micron was one of the first to introduce DDR5 technology, it's important to note that they were not wholly responsible for its creation. Innovations in DDR and RAM technology, like in other fields, are often the result of building from research of many others before them. Interestingly, this caused some issues for Micron and Samsung related to their sale of DDR5. This is really interesting because Micron and Samsung are two of the top 3 RAM producers globally. So to start off, a company called Netlist employs 2 extremely important researchers in the memory field. The first is Jayesh Bhakta and the second Jeffrey Solomon. These 2 researchers have produced patented research on extremely important areas in memory technology that was instrumental in the improvements that achieved DDR5. These advancements were so influential, in fact, that both Micron and Samsung were both successfully sued by Netlist for violating their patents to pay $445 million and $303 million respectively for violating the patents that in their production of DDR5. For those interested to learn more, you can find links to some of these patents that were violated by Micron and Samsung in the description below. 3 of the most important patents were 417B2, which covered memory module data buffering technology, 912B2, which covered memory module decoder technology, related to what we covered beforehand in our example of reading memory in DRAM, and lastly, the last of the 3 are 339B2, which covered memory modules with controlled bitwise buffer technology. In multi-core systems, each CPU core can have its own private cache. This setup can lead to significant issues with cache consistency. The primary issue is data inconsistency. When one core updates a data item, the other core might still have the old value in their cache, leading to stale data. This is a significant issue as modern computers continue to implement more and more cores, requiring more separate caches to search each of these cores individually. Imagine that both caches first take data from the address 0x0b, but then core 2 adds 1 to that data, as you can see in this image. Cache coherence protocols are designed to address these issues, ensuring that all caches in a multi-core system maintain a consistent view of memory. However, they can introduce some overheading complexity. One of the fundamental protocols is MSI, standing for Modified, Shared, and Invalid. This protocol uses 3 states to manage cache lines. First, it has the modified line. This cache line is modified and exclusive to one cache. It signals that the memory in this cache for this memory has been modified. The shared line represents if this specific memory is shared between different caches. And lastly, the invalid tag signals that this cache is representing memory that has been updated, and thus this cache is out of date or invalid. When a core reads a memory address, the cache line transitions to the shared state, if that memory is also in some other cache. If a core writes to a cache line and updates it, it has to transition the tag to the modified state. It then updates the main memory for that address's data. After that, the other caches holding that same address have to mark it as invalid. Then, when the core that is attached to that invalid cache data, when it tries to read that data and it sees an invalid tag, it results in a miss, even though the address was the same, but the data was invalid, so it forces the cache to fetch the modified data from the main memory. This ensures that only one core can modify the data at a time, maintaining consistency between all the caches. The MSI protocol helps manage cache coherence, but can introduce latency due to the state transitions and the need for cores to communicate cache states every time they're modified. Advanced protocols like MESI and MOESI add more states to optimize these transitions further. Cache coherence is vital in multi-core systems to ensure data consistency and optimal performance. The MSI protocol is a foundational approach to managing this, providing a structured way to handle cache states and maintain coherence across multiple CPU cores. Now that we've become experts in computer memory systems, let's quickly examine one very important area of immediate importance to programmers where we can apply our knowledge, specifically data structures. We're always told in our data structure courses that linked lists are best for writing, whereas continuous arrays are best for reading. With our newfound knowledge of memory systems, we know why this is. Recalling our principles of locality, let's think about how caching comes into play to help speed up reading from memory addresses that store continuous arrays. Of course, spatial locality is very important here. Because the elements of an array are stored in continuous memory addresses, they make use of rapid cache speeds as they are loaded into the cache thanks to the principle of spatial locality. In conclusion, we've explored the critical aspects of a computer memory system, from the roles of DRAM and SRAM to the importance of the memory hierarchy and optimizing data access speeds. We've highlighted advancements like DDR5, which significantly improve data transfer rates and bandwidth, crucial for supporting modern multi-core CPUs. Lastly, we also discussed challenges of cache coherence in multi-core systems and how protocols like MSI help maintain consistency and performance. Understanding these components and advancements is essential for appreciating the intricate design of modern computing systems. Recalling our analogy from the start of this video, would you rather be programming for an oil refinery with oil spills left and right, or an efficient refinery that properly handles the movements of its inputs and outputs? Thanks for watching.